sometimes an advantage, sometimes a disadvantage. Good, already the second presentation today. I think you will start, seeing that you have the microphone. You can read a bit what it's all about. So the other somewhere in the back close to our door was the tutor, or is a tutor I should say. He will hand out later on the diplomas. We will start with a presentation of say about 20 minutes. Then we have about 15 minutes or 20 minutes questions from the jury, mostly of the jury members, but other people can also ask questions. Then we have the handouting of the diplomas and then probably have 10 minutes left before we switch to the next room. So having said that in short, I would say go ahead and do the presentation as you would like to do it.
Thank you. Thank you for coming. Welcome. We are a group of third-year bachelor students, and we will show you guys how we brought retired aircraft back to the sky. First of all, do you know what happens when aircraft retire? Well, typically they go to a place like this, which is called an aircraft boneyard. The largest are in the United States, but we also have them in Europe, in Spain. First, I'll give you a little bit of context for our project. There are currently about 300,000 aircraft. This includes cargo, airliners, but also private jets. And this sector grows at about 3.5% each year. To be able to sustain this growth, you need a lot of material, especially aluminium alloys. And the primary process for creating these alloys costs a lot of energy and creates a lot of CO2 emissions. But you just saw the picture with a lot of aircraft, so you might think, why not just use those? Well, actually, they do use those. You can see that here. Yeah. So they scrap it, they dismantle it in a lot of pieces and then throw it all together and sell it as scrap. However, this creates an alloy that you can use to make a can of cola, but you cannot create a new aircraft out of this material. In the upcoming 20 years, approximately 13,000 aircraft will be decommissioned, so they will retire from the fleet. These aircraft now await a fate, as you saw in the desert. So, what is our goal? We want to create a closed-loop system. We want to recycle those aluminium alloys so they can be reused into the aerospace sector. By doing this, we create waste reduction, and as bauxite, the material of which aluminium is produced, has been added to the critical raw material list, we want to create more European independence, as we are highly dependent on nations like China for our aluminium right now. We also want to create a proof of concept aircraft. This is a Cessna retrofit to show how sustainable aviation can really be. So we will show how we actually use our recycled alloys in this aircraft. We are going to show that we met our goal by 4 requirements. First of all, we want to create a CO2 reduction of over 70%. Then we also want to reduce the embodied energy to 2.5 kilowatt hours per kilogram of aluminium alloy in the foundry process. So this includes smelting, decoating. This is also a 70% reduction to what it is now. Then we also want to be able to sell this aluminium for a competitive price, since otherwise, well, this project is not going to happen. And finally, we want to create the aircraft, the Cessna, so it has a similar handling to the current regular Cessna, so it can be sold interchangeably. Then a quick process overview. We start with dismantling the aircraft, so we create pieces that are approximately this large, and they are then decoated from a toxic coating so they can be sorted accurately, and after sorting, these pieces can be refined, so they'll be remelted and any contaminants will be removed, so we ensure a high-grade alloy. Then, with the sheets that we produce, we'll create the green Cessna, and we'll also go into operational flight of the electric Cessna. Finally, this all comes together in the business case, and first, Simon is going to tell you a bit about the aluminium alloy recycling.
Thank you, Roos. It's okay. So, thank you, Roos. As you just mentioned, most aircraft today are being downcycled, and this is quite a bad thing. Why are we not upcycling aircraft? Well, this is because it comes with a couple of major challenges. And our project is different because we are going to look at these challenges head on and try to tackle them. The first challenge is, how do we actually get these aircraft? We do this by setting up contracts with lessors and aircraft strippers. It's not exactly what you think. It's companies that take the cables, the seats, and the floors out of the aircraft and give us the raw metallic aircraft carcass. Next are 4 other challenges, the first of which is the fleet dismantling. We need to obtain evenly sized plates from these aircraft carcasses to be able to separate the different materials and the different alloys. So first, when an aircraft comes through our facilities, a mobile wire saw cutter will cut it, the wings and the fuselage into manageable pieces. Then a laser cutter will cut along the rivet lines that originally held our aircraft together. This is because the iron and the titanium present in the rivets would ruin our aluminium alloy. And the final product will be aluminium plates no bigger than 80 by 30 centimeters. The next problem is that these plates are coated with up to 3 layers. The inner 2 layers contain a highly carcinogenic substance called chromium-6. You might have heard it in the news a couple of years ago, as it was used on the coating in the tanks used in the Dutch military, and it created a big scandal. This is also the reason why some decoating techniques, such as laser removal or blasting the surface, are not considered, as it would put workers at risk. Instead, we will use a 3-step chemical bath sequence to remove all coatings. This is by bathing the plates in different alkaline solutions. Then we need to sort the aluminum alloy plates. This is so that the material composition at later stages can be predictable. If we wanted to sort every alloy type separately, this would become too expensive. So the 8 different alloy types are split into 2 groups based on similarities in chemical composition and how often they occur in airliners. These 2 groups are the 2024 and 7075 aluminum alloys, and this is because they are the most used in the aerospace industry. Our last step is melt refining. This is to ensure that our final product, the aerospace aluminum sheets, would meet the strict aerospace standards. So we will melt our plates to later be turned into the sheets. And our biggest issue right now is still the iron and titanium present in those rivets. This can be from incorrect removal of those rivets or other processes going wrong. To do this, we will dilute the melt. To solve this, we will dilute the melt with virgin aluminum, pure aluminum, or alloy aluminum. And this will decrease the element concentration to acceptable levels. There are also a lot of other contaminants, such as dirt, oxides forming during the melting, and, for example, sodium that will harm the final product. And these are removed with industry standard techniques. Now we have our refined melt, which we will solidify in 2-ton slabs that will then be outsourced to large-scale sheet manufacturers. So the key advantages of recycled aluminum alloys is that they use less energy and emit less emissions. We even had a hard requirement to use a certain amount of electric energy in all of the processes that I just presented, and this requirement was met. Furthermore, here are some numbers. Our process reduces the amount of energy needed by 58% and the amount of CO2 emitted by 98%. So not only do we have a recycled aluminum sheet, but we have a green sheet that also has the same mechanical properties as the ones used before in aviation. And Philip, what are we going to do with these sheets?
Thank you, Simon. So we are going to finish closing the loop with that retrofit Cessna that was mentioned. But let's take a step back. Why would we even retrofit a Cessna? Well, I think all of you know that not only the aviation industry, but the entire world is pushing for sustainability. And I'm here to show you how this retrofit can demonstrate that. Here is a nice illustration of some of the components that have been changed that we'll get to. But first of all, it demonstrates closed-loop aviation. From that retired aircraft, we can make a fully new aircraft. Then it also demonstrates the use of those recycled aluminium alloys that they can be applied in aerospace situations. And lastly, the retrofit will actually fit an electric propulsion system which has 0 emissions during flight, of course, sustainable. So what is the use case for an aircraft such as this? Well, to be specific, it is the Cessna 172 that we are retrofitting, and this is the most used training aircraft in the world. Training flights are very short and very frequent, causing a higher relative emission impact. So there's a lot to be won there. But how does our retrofit actually have the ideal use case for these specific training flights? Well, I have a short mission profile here, which you can see, which is basically that of a normal flight, but there are some practice maneuvers and a practice go-around to teach the pilot how to handle in those situations. And at the bottom, you can see how our battery would deplete with a short reserve. Well, turns out our retrofit has just enough endurance. As I will tell you later, there are some challenges with electric flying, specifically towards endurance, but it perfectly fits. Then, of course, far lower emissions, because not only the recycled alloy, but also electric energy. And with a recharging speed estimated to be around 30 minutes, this is fine for any operation that the Cessna will run on the daily. So, how will we use these recycled alloys? Well, the wing structure of this Cessna was actually redesigned, as you can see here. And to do that, we had to choose between those 2 recycled alloys that Simon just explained. And because those recycled alloys come from our own process, we can actually use a higher strength alloy to have less wing weight while increasing the wing loading, which is important because batteries are very heavy. So the wing was actually made a bit larger to accommodate for these extra heavy batteries. And then lastly, the idea is, of course, that this full structure that we have built can then once again be put back into our recycling process. Otherwise, we wouldn't really be closing the loop. So how did we electrify this propulsion system? Well, I said it enough. Batteries are heavy, very heavy. How can we fit them? Well, this chart should help you understand some of the challenges of fitting batteries into aircraft. At the left, we start with a new cell, which has all of its capacity. Then we have to fit it into the aircraft, losing some capacity. Ideally, you would not use the bottom and top percentages of your battery because this has some performance and lifetime issues. And then the last is, of course, degradation. Just as your phone battery gets worse over the years, our aircraft battery is exactly the same. However, like I said, due to increasing that wing weight and only needing to fly a mission profile of roughly 1 to 2 hours, we actually have enough. So what are then the benefits that we get from this electric propulsion? Well, 0 in-flight operating emissions. Then it is more than 200% efficient compared to original combustion engines, which lose all of their energy to heat. And 50% less noise. Even though most of the noise is made by the propeller of the aircraft, the electric motor is still far more quiet, especially in perceived noise. So, getting back to our requirement, this plane was engineered, even with the larger wing and electric propulsion system, to still achieve all the performance requirements needed to be that original Cessna 172. So, how sustainable aviation could be? Well, this Cessna retrofit gives us a massive CO2 decrease. Let's start again with the use of the recycled alloy. It has an 89% reduction in CO2 emissions during production. And then with those emissions that are not in flight, but only from producing battery replacements over its lifetime, we have an 83% reduction in operation emissions, which results in a lifetime CO2 reduction of 84%. So now Pietro will tell you more about the cost numbers behind our idea.
Oh, yeah. Thanks very much, Philip. There we go. So now we went through the technical solution to the problem, but we also wanted to evaluate the viability of this venture as an actual business. So how strong is this case? Can it hold up? Well, first of all, the environmental case, you've seen these numbers already, is really strong. We slash CO2 emissions as well as energy use. But one question remains, can we make money from it? Well, we focused on one central variable to figure this out. How many aircraft do we need to process every single year to turn a profit? And then from this variable, the costs flow down, and you can calculate all sorts of financial metrics, the initial investment, the operating expenses, etc. This is also kind of a two-way street. The costs of each part of the process will also determine how many aircraft you need to dismantle every year. There's also a very important part to take into consideration, is that number that you find realistic. Those 13,000 aircraft that we expect to retire over 20 years, that's around 650 a year. So say we were to find 1,000 aircraft, our break-even number, well, then it's simply not possible. Those aircraft do not exist. To situate this in time a little bit, that 20-year mark is when we expect this wave of retirement to end. And so because of that, we want to pay back our full initial investment within 5 years. Hence, a viability target for us is that 5-year payback target you see up there. On a plot, it looks like this. In purple is the discounted payback, and then in red you see that 5-year target. So where they intersect is our sweet spot. 77 aircraft we need to dismantle in 1 year, which is about 12% of those 650 every year. So it's very much a realistic number. Then, sorry, I was missing an animation. So 77 aircraft. Let's dive into the numbers a little bit more. One way to do this is a pretty crude, admittedly, profit and loss statement. So we have two revenue streams. One is the aerospace-grade aluminium sheets Simon was mentioning earlier, and then the second one is the scrap metal. What is scrap? It is simply all the metal that we cannot recycle all the way up to aerospace grade that we still sell for less demanding applications, which is, by the way, what is currently done now for those few aircraft that are even dismantled. We then have the other side, our expenses, operating expenses, so what it costs to run the business, and then the depreciation from the initial acquisition of all the machinery we need to make this run. And all in all, we turn a profit of about 2.7 million euros every single year. This, over 20 years, is about a 400% return on investment, and the profit margin is around 29%, which is remarkable, and it shows there is a lot of value to gain in those high-end applications. 29% is about 6 times what simple scrap earns you. We also wanted to figure out how sensitive are these results to variations, for example, in aluminium price, which as of lately has seen quite some volatility. So what if we take the aluminium price and knock it down 40%? Well, the minimum viable fleet we need to still make the business run only doubles. Of course, it's still a large number, but it's very much doable. And even more so considering aluminium volatility in 2025 only has seen the price shift maximum 25% instead of 40%. We can also look at what if we change the price of each of our processes and still changing the price by 20% or more only gives a 15% swing in the minimum viable fleet. So bottom line, it is a very strong and resilient case. Now, there is one last thing. There's still that Cessna that Philip was talking about. What if we sold that? Well, there's a case for it. It is cheaper than a conventional Cessna. It achieves more than 60% cost reduction in the EU and 20% in the US. This is due to gas prices in Europe being higher. Still, we would sell about 28 aircraft in a year from year 5, which we estimated based on simply the demand there is for such aircraft. And the issue comes with the fact that this only uses a few tens of tons of aluminium compared to the hundreds we produced. So this, coupled with a very hefty initial investment for certification and testing, makes us conclude that it is still not the best option. We're still much better off selling the aluminium sheets. Then, this was a lot. Let's wrap this up a bit, shall we? Where did we start? We started with retired aircraft, which we then disassembled, cut up into smaller, more manageable pieces. We then decoated them to get rid of all the harmful things that are put on them, especially the chromium-6. We sorted all of it into separate melt streams. We then remelted and purified the aluminium to make sure the alloys are in the right composition. And then finally, we can fly it again. A small recap also on the numbers of this case. We slash emissions by 98%, energy by 58%, and also an overall great deal of waste reduction. Otherwise, those thousands of aircraft would still have to end up somewhere, most likely in some desert. The financial case is also pretty strong. We can achieve a full payback in 5 years, and more than 400% return on the initial investment. And finally, it is also a key strategic project, especially in these uncertain times, bringing some critical material security to Europe and guaranteeing independence. So then, all of this being said, we can truly say that we're able to bring retired aircraft back to the skies. Thank you very much. And then a few thank yous are in due order. First of all, the rest of this amazing team. Also, guys, please come up to the stage. Our tutor, our coaches, and also everyone else that helped us along the way. With all the thank yous being said, we will take any questions you may have.
Then I'm going to grab your phone to give it to one of the people who's going to ask the question.
Yeah.
And then I walk through the room. Anyone who wants to start? Yes.
I think you can understand myself, no? You can hear me
Yeah,
well?
that's for the
For the
people
recording. Very good. So my name is Peter Winken. I'm a former student here. I work today in Airbus based in Toulouse. And so my question is all about what are the major trade-offs that you did during the course of your project? And is there one of them, now being at the end of your project, that you realize in fact that you should have done differently?
Yes, have a bit of thinking time, and I'm going to hand back the microphone. See, my job's to walk around. Anyone? Who dares?
So if I understand your question correctly, you're asking if there were any major trade-offs we did during our designing process that we... Which one they were, and if we would have done them differently.
And then at the end, is there one of them that you now that you know at the end of the story, we should have done differently?
Well, we actually did quite a lot, specifically for all the processes that we mentioned step by step, and we changed them a couple of times. So I hope to say that we are quite happy with the final solution. We had a different solution where, for example, instead of using a wire saw to cut the fuselage, we were using an abrasive water jet, but that created too much waste and other issues. So we actually looked back on that to use the saw. I don't know if anyone has any other examples.
Yeah. But there was also another one to remove all the rivets, because we do need to remove the rivets to take the pieces apart. Initially, we thought of punching them out, but it turns out some parts of the aircraft are too thick for punching, so then the machine gets jammed, hence why the laser cutter. So that's also an example. Would we go back on any one of them? I would say maybe not on the solution itself, on the technology itself, more so on the way it is implemented. So, well, time for this DSE was limited. But for example, the wire saw, there is definitely more detailed design work we could do to have something that is a bit more effective, efficient, and flexible. Does that answer the question?
Yeah, thank you.
Thank you.
Who can I give the mic? Yes. There you are.
Okay, well, I think that designing the Cessna in new aluminium was the easy part. The difficult part is, of course, this process. How much do you believe that you can actually get out these rivets in so many minutes and get it? How many rivets are there? Have you made an operational analysis of how much work it is? I mean, first you strap the aluminium, cabling. Somebody else does that. And then you get a carcass of an aircraft, and that is a large aluminium thing, and then you start cutting it, and then after that you get out all the rivets. How much work is it? How many rivets are there?
Yes, how many hours in these kind of things? Ah, here.
Yes, this question. So I mainly did the rivet cutting analysis. So first of all, we cut with the wire saw. That brings it down to about 30 manageable pieces. That takes around 11 hours, we calculated. And then we need to cut a lot of rivets. There are hundreds of thousands of rivets in an aircraft. And one thing we do is just cut along the rivet line, so not every single rivet is cut out, we just cut lines along the rivet line, so we remove entire rivet lines. And with that, we have to cut 11 kilometers of lines along the fuselage and 2 kilometers of rivet lines along the wing to retrieve the material was calculated. And then we retrieve around 11 tons. And it takes about 50 hours with a laser cutter to cut it all.
To remember the percentage
Per aircraft.
of the recycled aluminium alloy in comparison to the rest of the structure?
Yeah, so we only, back to aerospace, we only recycle 37% because of the rivets mainly. There are just so many areas around an aircraft where the rivet spacing is just too tight. And if a single rivet gets into your melt per kilo, it's almost ruined. So some areas were decided not to be able to recycle back into aerospace. But 37% are.
So you need a 747 carcass to build one Cessna 172?
We estimated 20 Cessnas per aircraft on average, and that's for mostly narrow bodies. Okay. So an A320 is about 20 Cessnas recovered.
Good.
Does that answer your question?
Throw away 19.
Throw away. It goes.
It's still scrap, so you can still use it for aluminum cans and stuff. You will drink out of it.
Okay. Thank you.
Good. Who can I give the floor to? Yes. Yes, she was there first.
Hello, Hilal van der Hoos from Pratt & Whitney. You mentioned you would use electric propulsion. How did you select your engine, and how did you take into account when you calculated your emission reduction at the end?
Yes.
You can do the motor, I will do the emissions.
Yeah, so the process basically started with determining that mission profile. So we had an idea of what to design to, specifically in terms of endurance. And then, of course, first class sizing to get an idea of the power necessary and all that stuff. And then you basically go shopping until you find an engine that has all your requirements. And we found an engine that is actually only 16 kilos with a gearbox and an inverter, and has more than enough power to power the Cessna forward. I think Jesper can tell you a bit more about the emissions.
Yeah. So the second question was, how did we calculate the emissions? So we used the calculations from the structure, from the foundry process for the aluminium, for calculating the structural influence on emissions. And then we also used the emissions made by creating the electricity for the Cessna to add that. And then we add the battery emissions during the mate of the batteries. And then we added up and we found the life cycle emissions of the Cessna. I hope this answers your questions. Yeah.
Kjeld first, and then I'll go backwards again.
Yeah. Hey guys, thanks for the presentation. For passenger safety, it's always required to have your materials qualified. I just wondered if you've looked into that, whether you've taken the cost of that into your economic model, and do you see any challenges on that?
Nice, short but annoying question.
So the challenge we thought we had was recertifying, but because we make our material into the 2024 and 7075 alloy, there is no certification at all needed for the aluminium, because it's already within the bounds, so it's just certified as that material, so we can just give it to our manufacturers and they will just use it as every other material. I hope that answers your question.
Maybe I can add on to that?
Of course.
So of course we have in-house testing during the refining, but also for every batch, samples are sent to a testing facility, so that is outsourced. So we do have costs of that since we don't do it in-house, but those are fairly limited. We decided not to create an in-house testing facility because we thought it would be better to have outside, and also for costs, and it would be weird to certify our own material.
It's good to see you thought about it. I can maybe also follow up.
Okay.
Thank you. So actually the product that we that we got from this recycled aluminum alloy that we are using for was the Cessna. So we then had to design a product with those considerations in mind. with the variation in the strength, in the properties. And initially we had to design for the sort of a worst case scenario of those material properties. Those material properties will have some range of, let's say, volatility in them. So the structural itself could also be, let's say, optimized if we had more statistics to have idea of how big the variations are. But for now, it was very conservative. It was the worst case scenario for the yield strength, worst case scenario for the fracture toughness of the structure. Thank you.
I already saw another question there a bit in that direction. Yeah, you can give one to him as well. Hey, yeah, of course.
You mentioned you had to reinforce the wing structure because you placed batteries inside. Shouldn't the batteries alleviate some of the wing loads?
So the question was if the batteries in the wing would reduce the loading. I don't believe we place any batteries in the wing. And the reason for this is also because of the space constraints and the difficulty packaging in there. And the wing loading reduction would also complicate the structure in some ways because of the compressive strength within the wing being the main limiting factor that is influencing design. Our internal wing structure was primarily governed by buckling of the skin panels, and therefore the reduction in the weight wouldn't have benefited much compared to the complexity. Maybe Piotr wants to add a little.
Yeah, also, to make the connection to the battery, you did mention, well, the original Cessna has fuel tanks in the wing structure. We don't have that, so that was actually already a challenge in itself. The wiring from the wing to the fuselage of the batteries would also be quite problematic. Therefore, no batteries were placed in the wing as well. Lastly, in the no, there was one point I was trying to make, and I completely forgot about it. Yeah, maybe if it comes up to my head, I will tell you maybe in a minute. Sorry, there was. Yeah. Okay. Yeah. Sorry. No, that's perfect.
Otherwise, I'm going to pass on again. Anyone a question? Yes, I'll walk that route again. Yeah, although I have a question for myself if needed as well. It's not that difficult.
As a team, could you explain a bit how you organized and structured yourself and how you ensured as a team that you were making the right decisions?
So something on the internal process.
Yes. So the question was, how do they organize each other, organize ourselves and make the right decisions? Well, we split up the group after the midterm. So after week 5, we split into 6 people on the foundry process, so mainly the aluminium, and 4 people on the Cessna. And every week we had talks with our supervisor, which we also prepared for, so we shared our ideas. And every week we also had internal meetings where we presented what we were thinking of, so we could give feedback on each other. Of course, you're confined to one space the entire day, so you also bounce ideas off of each other. But having these structured moments, I think really helped us to, help each other. I think those were our main approaches. Is that okay?
Let's see the time. So we have a bit of time left. So. I hope I can bounce back to that. Yes, of course. You had a bit of time to think about it, and now you know.
To structure it fully. So batteries in electric, let's say, propulsion in electric vehicles that are flying are actually key issue. The batteries themselves, they don't lose weight over the length of the cruise, such as the fuel does. That was also a concern that we also took into account. And the driving requirement we also have placed to make the Cessna retrofit was a 10% increase in maximum takeoff weight. That was our driving requirement because we thought, okay, we are going to place batteries in our aircraft. We need to have more bearing capabilities in the lift. And so that was the idea. That was the, let's say, the requirement we drove forward to. And that it resulted actually in a bit of an increase in the wingspan as well. More lift, less for the more mass of the batteries that stay constant over flight. I hope that answers your question fully now. Thanks.
Good. Other questions? Yes.
Well, at first I was a bit concerned about alclad. You were showing how an aluminium sheet is built, but then you said we add pure aluminium to the melt, so you can leave the alclad there, or did you consider that?
Yeah, so where does the pure aluminum from the alclad go?
So in the case I explained, the pure aluminium is in a dilution process. This is just to lower the element composition to acceptable levels. There are, for example, cladding on top of the sheets. This is an industry process. This is included in the processes that are, for example, for the sheet manufacturing.
Okay, but you can leave it on. You don't have to remove the cladding.
Oh no, well, we are melting the plate down, so it is just not there anymore. So when we produce the sheets, we will add the cladding again. Does that answer your question?
Yeah.
Thank you.
Good. Any other nice questions? Yep. That's good. I'm happy.
Coming back to the Cessna, you quite drastically changed the characteristics of the aircraft. You change engine, you change the weight of the engine, you add batteries, you don't have the fuel. How did you assess the overall aircraft design, performance, the recertification of that hybrid Cessna, I could call it?
So in redesigning that Cessna to take all those performance capabilities into account, important was not only the amount of power needed by the engine, which actually, after the redesign of the wing structure to increase for that takeoff weight of the batteries, gained some performance benefits. The engine barely needs to have a higher power output compared to the original. And then the batteries are placed in two positions in the fuselage, near the motor and after the passengers, to balance the CG within the original limits. And then all performance characteristics such as stall speed, takeoff distance, landing distance, rate of climb were all calculated with our new Cessna, and all requirements were at least the same or better. There was one takeoff requirement, which was an issue, needed a 1% increase in takeoff power, which the engine could provide. Does that answer your question?
Yep. Yes. Back we do diagonal walking today.
Well, the lifespan of the aircraft, you will see that you get a lot of fatigue on this Cessna because it's going up and down, up and down, up and down. But what about the batteries? Did you consider the fact that you may have to change batteries during the lifetime?
Yeah, we considered that. We said that we want a degradation until 90% of the batteries, because then we can still fly all the full flights. So we change them 10 times. Yeah, so it's quite often,
like
but
your mobile phone,
yeah,
it's the first thing that dies.
but we sell them afterwards to other companies in the second-hand market to still have them. Yeah.
Also, that's
2 years. It's like roughly 1,200 cycles. But yeah.
Might be that the pilot is dying earlier. You never know. Good. Any other questions? If otherwise, I had one question because I saw that you had quite a decrease in energy use. Is that the energy, basically you get electric energy? How did you create that electric energy? Is that also in that thing? So if you burn oil, is it great that you just shift your boundary and you don't take it into account? So that's a window dressing, but how did you get the electric energy in? Where does the electric energy come from?
So we didn't mention it, but our process is based in France for multiple reasons. And so for the energy, we used the energy from that country, which is specifically green. They use a lot of nuclear energy, a lot of renewables energy. So that's where it comes from.
Yeah, and that's the reason why you can save energy. Because that was normally, if I have a heavier aircraft, I ultimately think I need more energy to fly. I can't imagine that you use less energy, but on the whole picture, it's still less.
Yeah, sorry?
Yeah, so the aircraft doesn't use less energy, the aircraft emits less carbon, carbon equivalent. But because it uses the recycled aluminium alloys where less energy is embodied, that's how it uses less energy.
Good.
Yeah.
Clear then. Thank you. Any other questions? Yes, I think the final one.
Did you make any analysis of this recycling process itself to understand the energy consumption and the process itself? Because we aim to reduce the emissions or energy consumption of our design with a lot of assumptions, but actually the processes consume a lot too. So what kind of analysis did you do? What were your references?
Yeah, so comparing to the other way to manufacture aluminum, I guess.
So if I understand correctly, you're asking how did we analyze the energy used during the recycling processes? Yeah. So we have multiple steps. So for example, we have the dismantling, decoating, sorting, and the refining. And even in those steps, they're split up into multiple sub-steps. We looked at all of these, also at reference infrastructure use, and we calculated the energy required per kilogram of aluminium, but also maybe per year if a machine is running 24/7, and that's how we calculated the total process costs. Does that answer your question? Yes?
Good.
Based on literature. Yes.
Good, then I would say thank you for answering all the questions. And the next step in today is that we will hand out diplomas. Not all of you. Some of you apparently are lacking a few courses here and there. The aim is that we have everyone getting a diploma, but I know from reality that's never happening. We have Santiago, your tutor, who will do the honors and give you some nice diplomas.
Very good. Yes, well, thank you very much. So first I would like to maybe ask Max and Manu, who were the coaches also in the project, to come forward. Maybe a short thing, so you can see that I'm the shortest and the most informal one, so I should definitely be the supervisor. But I would say that the team worked extremely well. And I would like to give a couple of words there. I actually wrote 20 pages, but I don't think I have time. So some of the things I wanted to say. So first, a bit of introduction on the topic. So I'm associate professor at the Department of Aerospace Structures and Materials, and in my team we work a lot on materials and surfaces for sustainability. So we think about how to make processes more sustainable, and also the end of life. So end of life also fits there. And one of the things is actually with aircraft, and I think the team explained it very well. Right now, aircraft are not recycled to the level of aerospace alloys. So actually we lose a lot of value. European Union, with the Critical Raw Materials Act, is actually pushing Europe to try to find as much as possible materials, raw materials, resources in European soil. And one of these actually strategies is to try to recycle to the high level everything we have. Until now, there was a lot of doubts if this process of taking aircraft and then recycling it to a aerospace-grade aluminum alloys was economically viable, technologically possible, and even with a business case at the end of it. So I think that you can already take this, that the students have actually shown that this is actually an interesting opportunity, which we have to be looking a bit more in detail from engineering perspective and material science perspective. So it's actually pretty good. Maybe about the team. I didn't know the team members until this moment, although I remember some faces and some names when I was teaching in the Bachelor Material Science course. I asked the students if which were the preferred bachelor courses, so I have this information now, and also which were the least preferred courses. Okay, so fortunately, none of them mentioned materials as the least preferred one. Unfortunately, only one mentioned it as the second best course. So it's okay, but you know, they are not perfect. They are very good, but not perfect. I think they did a fantastic job, all the team. They've been interacting a lot with them. We learned a lot about them as engineers, young engineers. They like to do memes in the process. We managed to see some of them. I'm sure we didn't see the best ones or the most critical ones. Maybe one day we will see them. We know they do a lot of sports, and actually the absolute winner is rowing. And actually it was quite a nice thing to do in the sport, because they actually row together towards the end of the And that's actually very necessary in this thing, because indeed they had this structural management, internal interconnection between teams and so forth. Extremely well done also by there. Now the solutions are nice, and there was actually a lot of industry involved. You didn't mention it, or I didn't hear it, but there were actually several companies that actually were very happy to discuss the topic and the ideas with them, and to be actually extremely interested of the final solutions they could actually find. So you can see that this DSE is actually for them to also realize this is a DSE that can potentially have impact in society. And that's actually something that you don't see every day. So I will actually, again, thank the team and also the coaches because of these fantastic 10 weeks. Very hard work, very hot weather today and this week, yes. But you managed, so it's actually very good. Now with this, well, yeah, you can applaud, yes, sure. Do you have the names? Okay.
You can just go from 1, 2, 3.
Very good.
Yes.
Okay, so in 17 years, this is the first time I do this event, so I'm actually very happy that you are the first ones. Okay, we go then with names, and yes, it was mentioned that not all of them would get the diploma today, but they will get it in September because of, funny enough, sometimes some things in the underlying timing are not perfect. So, but they will get them, so that's for sure. And I would like to start with Philip, and I would need to say, Philip, where are you? All the name? Really? No? You want it? Philip Helmuth Ari Benschop. Very good, congratulations. And you can come forward. Congratulations. Yeah, move on. You want to have, yeah, if you, I saw so many cameras that I didn't dare to ask.
I'm going to give you this
that's a good point.
bag, basically, which you can use for storing it.
Thank you very much.
And
yes.
Enjoy it, and of course...
Enjoy it. Maybe I didn't mention it, but this young gentleman also started a dream team, and it's actually a really nice, impressive thing to do together with the DSE, so really nice. Okay, guys, we move forward. Next one would be, oh, this is easy here, Pietro Cartocci, come on. Congratulations. Very good, photos and these kind of things. And again, enjoy it. Don't fold it. It's very good. Okay, we move on. I'm looking at the time, sorry, but okay.
You already eaten some time there.
Yeah, I'm eating time. They know me, the same thing. Okay, anyway, we go on with the next one, Roos Willemijn van Duin. Gefeliciteerd, hè? Ah, I'm finally asked. Oh no, sorry.
Finally, you're large.
Yes. Very good. Congrats. Okay, we move on to Theodor Johannes van de Grint. Yay, Theo. Congratulations, man. Well done. Cool. Yes. Looks total different in person, right? If I'm standing here. Okay, yes, it feels good. I mean, okay, let's go for Simon Edgar Yeh. Who waard? Hey, congratulations, man. Well done. Yeah, come here. Oh, wow. Yeah, you need to be lower. Yes, well done.
Thank
Super.
You.
And we have 2 more to go. Quinten Andreas Nouwens. Very good. Oh, quite funny. Congratulations, well done. Super cool. I will be now here. Very well. Well done.
Good.
And the last one, not the least. No. Jesper Dan Smits. Very good. Congratulations. Super well done. Now I need to be up, huh? Now we yes. Where do we need? Super. Okay. And yeah, here we finish this this DSE group. Next time more.
Now give yours to me. Good. Thank you for being here, asking all the nice questions. The jury members will continue to go to some other room probably, and the rest is spreading out and seeing all the nice discussions as well in an hour. Eat some things, drink some things. That's all part of the plan. And yes, we are lovely on time. I have to talk for 2 minutes. I won't, because I'm just going to stop and they say, go walk around and we'll see who comes next in this room. Thank you. Good.
Thank you. Yeah.